Hi everybody, this is Dr. Bricker here with some homework hints for homework number 5. So the first one is magnetic field at the center of a 1 centimeter diameter loop is 2.7 milliteslas, so 2.7 times 10 to the minus third teslas. What is the current in the loop? And then part B, a long straight wire carries the same current. At what distance would is the magnetic field 2.7 milliteslas? You might have different numbers, so be careful. Let's take a look at this one. Okay, so we know that the magnetic field for a loop is mu 0 I over 2r. So in this problem, they give you the magnetic field strength, so you know that. They give you the diameter, and you need half that for the radius, or if you notice here, 2 times the radius is the diameter. So if you get the diameter, you're going to have to multiply it by 2 anyway, so let's just leave it as 2 times r. So we need to solve for I. Multiply both sides by 2r. So multiply both sides by 2r, divide by mu 0, and that will give you the amount of current that you need. So so you make sure you look up what mu 0 is. I'll leave that to you. This I turned into meters here, which is what we need. We've got teslas there. So that's the first part. That'll get you started. And part B is, if you have a long straight wire with this same stuff that you have up here, how far away from the wire are you to have this magnetic field with this amount of current flowing through it? So a long straight wire has a different formula. Mu 0 I over 2 pi r. We want to solve for r. So we need to get the r over here and the b over there, so we can switch those around. R, then bring it over here. Mu 0 I over 2 pi b. And then that'll give you the distance away from the wire. Same thing, mu 0 is the constant. I you use from the first part, 2 pi, and the same thing you use b from the first part to figure out how far away you are. Okay, let's look at the next one. Okay, the next one, consider the wires shown here. And we know I1 is 20 amps. Okay, good. So I1 is going to the right. And we want to know, what should current I2 be? I2 is also going to the right in the lower wire, such that the magnetic field at this point is 0. Okay, let's sketch it out and see what we can come up with. Okay, so I did this in 2 different colors. You'll see the reason in just a second. First of all, we need to know at this point here, are the magnetic fields working together or are they opposing each other? So right-hand rule for I2, I2 is going to the right, so the magnetic field is out at you, everywhere above it. And then down here, on the other side, it must be going into the page. So that's into the page, that's out of the page. Let me take that back, actually. Let's take a look at this again. Here's I2. Everywhere in between, it's out at you. I think I said that, but I drew the wrong symbol for everywhere it's out at you. It looks like this, right? Something like that. And then on the other side, it's into the page. Into the page is this symbol. Okay? So everywhere above the wire, it's coming out at you. Everywhere below the wire, it's going into the page. That's because of I2. And then for I1, everywhere above the wire, it's coming out at you. And then when you're below the wire, by below I mean in this region, if you put your thumb in the direction of the current, I had to stand up to do this, everywhere here, it's into the page. Okay, so they actually are opposing each other in between here. That's why the magnetic field could actually add up to 0. Okay, so the magnitude has to be the same. The magnitude because of B1 is equal to the magnitude because of B2, and then they can actually cancel out. So mu 0 I1 over 2 pi R1, and this is what I'm calling R1, 1 centimeter. It's got to be equal to mu 0 I2 over 2 pi times R2, and R2 is 2 centimeters. So usually you change things into meters, but if you left them both in centimeters, you'd actually be okay because centimeters and centimeters would cancel out. 2 pi's actually cancel out. And then from this you can figure out what I2 is. The mu 0's actually cancel out too. So I2 would have to be I1 And that would then give you R2 over R1. And then that makes sense. If you got 20 amps really close, you're going to have a lot more amps when you're farther away to have the same magnitude of magnetic field. Okay? So get the number for that and then take a look at it, and I think it'll make a lot of sense to you. Let's look at the next one. Okay, although the evidence is weak, there has been concern in recent years about possible health effects from the magnetic fields generated by transmission lines. Okay, we know magnetic fields are created by currents now, so we want to see what the amount of magnetic field actually is for a given current. So a typical high voltage transmission line is 20 meters off the ground and carries 200 amps. Estimate the magnetic field strength on the line below it. So treat this as a long straight wire, mu0 times I divided by 2 pi r. Here they give you the I, the 100 amps, and they give you the distance away, the little r in the formula, 20 meters, so you can figure out what the magnetic field is, and then they want the answer in microteslas. So convert it to times 10 to the minus 6th. And then we want to know, how does that compare to the Earth's magnetic field? So whatever you get from part A, divide it by 5 times 10 to the 5th, multiply that whole thing by 100, it'll tell you the percentage of the Earth's magnetic field. So you're figuring out the magnetic field because of the wire. How does that compare to the Earth's magnetic field down here? Okay, all right, good. Let's see what we have next here. A solenoid, okay, so that's a different shape. You've got to think, what's the formula for magnetic field because of a solenoid? We know what that is. Used to produce magnetic fields for research is 2.2 meters long, inner radius 28 centimeters, 1,300 turns, producing a magnetic field of 1 Tesla. Okay, so that's sort of an MRI, a standard kind of an amount. And we want to know how many kiloamps. First of all, we don't need to know what the radius is. The radius is not even in the formula. They just give you that information. You don't actually need it. Again, if you forgot what the formula is, you could hit review here. It'll go to that section in the book. But let's take a look at this one. Let's get it set up anyway. Okay, so for a solenoid, we have this formula. Now everything's given except for what you need, so this won't be too bad. We need to get I by itself. So B times L divided by mu0 N will give you the amount of current. Okay, and then you'll have to change it to whatever they wanted. I believe it was kiloamps. So kilo means times 10 to the 3rd amps. Okay, very good. Now, if you notice, all these formulas for magnetic field strength always have a mu0I in them. And then there's something else, like this one has the amount of turns divided by the length. And again, no radius involved. Let's look at the next one. Okay, so this was kind of covered in the content part. So go back and take a look at that. Chapter 24, part 1, I went over something very similar to this. Next one. Experimental tests have shown that hammerhead sharks can detect magnetic fields. In one such test, 100 turns of wire are wrapped around a 7-meter diameter cylindrical tank. Magnetic field was created inside when the coil carried 1.5 amps. Sharks trained by getting a food reward when the field was present would later unambiguously respond when the field was turned on. So they're detecting the magnetic field. What is the magnetic field strength at the center of the tank? So we did a similar one also in the chapter 24, part 1, where we looked at the magnetic field created by a similar tank for green turtles. Okay, so you got a loop of wire. That's what this problem is, a loop of wire, 100 turns, and we know the diameter of it, and we know the current that's being carried. We want to calculate the magnetic field. And then part B is here, how does this compare to the Earth's magnetic field? So the Earth is like 5 times 10 to the minus 5th is what you get there, bigger or smaller. I would say, my guess would be, if the sharks are responding to this magnetic field, it must be bigger than the Earth's magnetic field. But let's take a look at the formula, and then I'll leave it to you to put the numbers in. Okay, so for a loop, here's the formula we have, mu0. This is the amount of loops. So this is something that's not really wide. This is just loops that don't take up much room when they're spread out. It's just, it's way thinner than a solenoid. So we got mu0 N times I divided by 2R. So in this problem, we're given the amount of loops, we're given the diameter, and we're given the amount of current. So the formula has, again, radius here, but it's 2 times the radius. So this thing is actually the diameter. If you want, you can get the radius of the circle, 3.5 meters. That's fine, but then you're going to plug it back in anyway. So this is kind of a straightforward one where they're asking for B. You have a formula for B. Just put it all together and solve for the magnetic field strength. And then see how that compares to the Earth's magnetic field strength. Let's look at the next one. Okay, a proton moves with the speed of 1 times 10 to the 7th. Okay, so it's a proton, you know its charge, 1.6 to the minus 19th coulombs. And we know its speed in this direction shown. Here is the strength of the magnetic field that it's involved in. So this is some external magnetic field. And then we want to know what is the magnitude of the force on the proton. So let's see, a 0.5 Tesla magnetic field points in a positive x direction. Okay, so the magnetic field is this way. Okay, and then we're seeing the direction that this is moving. So maybe I'll just take a look at the first one, and I'll leave part B. I think there's just a part B. Part B and part C. We want to know in part A, what's the magnitude of the force in this picture, and then what is the direction of the magnetic force on the proton. Okay, so the force is always perpendicular to the plane made by the speed, the velocity, I should say, the velocity and the magnetic field strength. Okay, so we know it's a proton, so we know the charge, 1.6 to the minus 19th. We know how fast it's going, 1 times 10 to the 7th. And we know the magnetic field strength, given in the problem, of 0.5 Teslas. And we know the magnetic field is this direction. And we know the proton is moving this way. So there's an angle between V and B. The easier problems are when V and B are completely perpendicular to each other. Then it's in the formula QVB, sine of the angle between V and B. So when the angle between V and B is 90 degrees, the sine of 90 is 1. That part goes away. But here there actually is an angle between V and B. They give you it as 45 degrees. So to get the force, it's the magnitude of the charge, which we know, the speed, B, and then the sine of the angle between those. So when you put that all together, you can get the force, and don't be surprised if it's really small. It doesn't mean that the proton doesn't feel it. The proton's mass is times 10 to the minus 27th kilograms. So even this small force that you get here will be felt by the proton. To get the direction of the force, you use the second right-hand rule. So you got to line everything up and then figure out the direction of the force. Now, it might be kind of hard for you to see this on the screen, so take a look back at the book, but basically you put your thumb in the direction of V, and then put your pointer finger in the direction of B. And remember, this is in 3 dimensions, so like the y-axis here you could think about is actually big into the page. You get the direction of the force. So in this example, the force is in the positive y direction. It's hard to draw this all in 3 dimensions on a flat piece of paper, but this is x, this is y, which is essentially into the page, and then z would be this way. So when you do the second right-hand rule, you have to line those things up. And when you do that, you'll see that the direction of the force is in this direction. Now, part C is V is one way, B is the complete opposite way. You have to ask yourself, well, is there even a force if that happens? Okay, let's look at the next one. Okay, this one is similar to what we just did. You have the direction of V, you have the direction of B. It's an electron, though, so keep that in mind. It's the same formula, but the angle between V and B is 90 degrees. So sine of 90 is 1. That part's not so bad. Now, when you use the right-hand rule to get the direction, this is an electron. So use the right-hand rule, get the direction, but it's a negative charge, so the direction of the force is actually exactly opposite. So use the right-hand rule like you usually would, but then realize, while this is an electron, it's a negative charge, direction of the force is the opposite direction. All right, let's look at the next one. Let's see. An electromagnetic flow meter applies a magnetic field of 0.2 Teslas to blood flowing through the coronary artery at 15 meters per second. What force is felt by a chlorine ion with a single negative charge? Okay, so what force is felt by this? Let's take a look at this. Okay, so it's a moving charge in an external magnetic field, so it's going to experience a force. Similar to the last couple of problems, they give you the magnetic field strength, they give you the speed in centimeters per second, so you've got to put it into meters per second, divide by 100, or move the decimal point over 2 spots. Now they say it's singly charged, so here's the magnitude of the charge. This is the magnitude of the charge. 1.6 to the minus 19th coulomb. So somehow an electron has been added. Now we're going to assume that the angle between V and B is 90 degrees in this problem. So it might be something like, here's a negative charge moving this way, and there's a magnetic field here. The magnetic field could be into the page or out of the page. So let's just say the magnetic field is into the page. We can figure out the direction of the force on this negative charge from the right-hand rule. If you use the right-hand rule, the force would be to the left, but it's a negative charge, so the force would be to the right. And then you get a buildup of negative charge over here, lack of negative charge here, and then there's actually a voltage difference, and you could measure the voltage, and from that deduce how fast blood is flowing. So you don't have to actually cut into the artery or the vein. You could just measure the voltage across this, and it's proportional to how fast blood is actually moving. Okay, but as far as this problem goes, it's kind of a straightforward one in that they're asking for the force. Here's a formula that says force is equal to something. Everything is given. Just put this in the meters. Singly charged means this. And again, assume theta is 90 degrees, some kind of scenario like this. Okay, let's look at the next one. Okay, so here we go. You can take a look at a similar problem solved by the author of the book here just by clicking on Video Tutor Solution. So current is flowing through this wire. There's a region of a magnetic field, 10 centimeters wide. We know the mass of this wire, 2 grams, and what magnetic field strength will levitate this wire. So gravity's pulling straight down. You can actually have a magnetic force that's up, and that would balance the weight. So that's what they're asking here. And then part B is, what is the direction of the magnetic field? Okay, let's take a look at it. Okay, so here's the scenario. Now, current is moving charges. Moving charges in a magnetic field experience a force, so this wire is going to experience a force. Here's the magnitude of it. Current times the length of the wire that's been exposed to the magnetic field field strength, and then the sine of theta. So in this problem, if we did the free body diagram, we would have the magnetic force up. This is the magnetic force. And then we would have the weight down, and they're balancing each other. So magnetic force is equal to the weight. And then I could put in what each of those is, I, L, B. Now, in this picture, to have the minimum amount of current needed, the magnetic field would be perpendicular to the current. So the magnetic field's either into the page or out of the page. Regardless, the sine of 90 is 1, so that part goes away. Sine of 90 is just 1, so 1 times this quantity just gives you the same quantity. And then that's equal to mg. Okay, so m we know, g we know. The magnetic field is the part that we're looking for. The length we know, that was just 10 centimeters. Make sure you convert that into meters. So divide this by 100 to get 0.1 meters. And then the current we also know, given in the problem, 1.5 meters. So a little bit of algebra here. Divide both sides by I and L. And then the G, thinking back to physics 220, 9.8 meters per second squared. Okay, so mass times G divided by IL will give you the magnetic field strength. So if the weight is down, we need the magnetic force to be up. So you have to use the second right-hand rule, rather, to figure out which direction the magnetic field is. Here's a hint. It's either into the page or out of the page. So line up V. V is the direction of the current. So this would be V. That's where your thumb goes. Your pointer finger goes where the magnetic field is. And then the rest of your fingers, that's where the force is. So you don't know what B is. You've got to line up V and F, and then whatever B turns out to be, that's where it's at. Okay, so be careful with that. I gave you a hint, in or out, and use the second right-hand rule to get that. All right, let's look at the next one. Okay, so a current loop in a motor has an area of 0.75 centimeters squared. Be careful, we're going to have to change that into meters squared, and it's a little more complicated than you might think. We know the amount of current, and we know the uniform magnetic field. What's the magnitude of the maximum torque? So if you forgot that, again, I say this, but let's actually see what it looks like. Let's take a look at this. So I clicked on that link. It's going to take us to the part of the book that we need. And the formula should be here somewhere. Current loop in a magnetic field. It's a nice picture of a motor. So a motor is you provide the current, and then out of that you get some activity. In this case, this loop of wire will actually rotate. Okay, so here's the formula for torque. That symbol is tau, by the way. This is tau. So torque, in other words, tau, IAB, and then the sine of the angle. And that angle is between B and the area of the loop. So sometimes this I times A is called the magnetic dipole moment, and people write it as mu. So I times A is equal to mu. Anyway, what we need is torque IAB sine of the angle. And they say maximum torque, so the angle is 90 degrees, so we're getting the maximum torque. Okay, let's go back to the actual problem. Okay, so there's our formula. Theta is 90 degrees, so the maximum torque is just IAB. Okay, I is 240 milliamps, so 240 times 10 to the minus third amps, or if you want to, you could write it as 0.24 amps. Be careful, you might have different numbers. 0.62 Teslas, that's good to go, that's in Teslas. Now this 0.75 centimeters squared, we need to put that into square meters. So 1 square meter would be 100 centimeters times 100 centimeters. So you have got to divide this by 100 twice to put that into square meters. But then you're good. You just got to do a little bit of prep work. Put that into amps, put this into square meters. For maximum torque, theta is 90 degrees. Okay, let's look at the next one. Okay, so an electron travels with a speed of 9 times 10 to the 6th meters per second between these two parallel plates. The plates are separated by 1 centimeter. So basically, this electron is flying between into a capacitor. The plates are separated by 1 centimeter, charged to 200 volts. Okay, good. What magnetic field strength will allow the electron to pass between the plates without being deflected? And what's the direction of the magnetic field? Okay, so this is something called a velocity selector. Only an electron with a certain speed will fly right through the center of this thing. And given the speed, we want to know what kind of magnetic field we need to have for this to actually happen. Let's take a look at this. Okay, so here's the electron flying into this capacitor. I added this little part at the end here. There's a plate here and a plate here. Now, there's a little slit in the plate, and only an electron with the correct speed in this kind of magnetic field will go right through. Something else, if the magnetic field wasn't strong enough, they would land over here and not make it through. If the magnetic field was stronger, they would land over here and not make it through. So this is a velocity selector. Only certain velocity electrons will go right through this. So inside here, there's an electric force that's this way, and that's equal to Q times E. That's what we did before. Now, if you can supply a magnetic field, that would be down. I'll just put F magnetic, which is QBB. You could have those balance each other, and this electron would fly right through this thing. Okay, so just a minute, we'll talk about the direction of this magnetic field. The magnetic force, we know, has to be down. So the electric force magnitude is equal to the magnetic force. This is equal to QE, and then this one is QVB. Now this V is the velocity, it's lowercase v. Okay, the Q's actually cancel out. So the magnetic field that we need would be electric field divided by the velocity. Seems kind of weird to be having those in the same formula, but we'll see how that works out. And then this is equal to B. Well, they don't give you the electric field, but they do give you the voltage across the capacitor and the plate separation. So going back to a previous chapter, maybe I should have called this the voltage across the capacitor. That's what I meant by that. Anyway, the voltage across the capacitor is E. See, is it times D or divided by D? We could just look at the units actually. E times D, yeah. So how did I do that? This would be, the electric field is measured in volts per meter. So for the units to work out right, I knew this had to be E times D. Okay? So then the voltage across the capacitor divided by D will give you E. Why am I doing that? So I could take this and plug it in here, and then I could actually do the problem. Okay? So now if you want, you could do it at this point, figure out what the electric field is, voltage across the capacitor divided by D, and then plug it in here, or we could take this and plug it in right now. So electric field, voltage across the capacitor divided by D, that's what E is, and then there's still this velocity hanging out. Okay, so that would give you the magnetic field strength. Okay, so make sure that this this plate separation is in meters. The velocity is already given in meters per second. It was an electron. There's the magnitude of the charge, but we don't actually need it because the charge cancels out in this problem. Okay, good. So that's how you should be able to get B. Then you've got to decide, well, which direction is B? Is it into the page or out of the page? Same thing, like a couple of previous problems. Use the second right-hand rule. You know it's moving this way. You know the force is this way. Which way does the magnetic field have to be? You've got to line your fingers up. Thumb in the direction of V, pointer finger with the direction of B. Actually, you could write it on your finger like this. V, there's the force, here's V. Now you keep these all perpendicular to each other when you line them up. So the ones that you can pick now are V. You know V has to be that way. Your thumb has to go this way. The rest of your fingers has to go that way. Which way is the pointer finger? And again, hint, either into the page or out of the page. Okay, let's look at the next one. Okay, so this is sort of like a mass spectrometer. This is a mass spectrometer, actually. It's a version of it. There's several different types. This is one type. You have a sample of unknown composition. A first step at analysis might be a determination of the masses of the atoms and molecules in the sample. A mass spec to make such an analysis can take various forms, several different ways. But for many years, the best technique was to ionize atoms, send them through a magnetic field, and see what the radius of curvature of their path would be, actually. Okay, so you might have a stage up here where you select certain velocities, just like we did with the previous problem of velocity selected. So you know the velocity, you know the charge, you set them through this path. Different masses will have different radii then. You have a detector over here, and this will detect how many masses hit here. You might have another detector later on detecting more massive particles. You can get the ratio of lighter to heavier, that sort of thing. Okay, very good. So in this spectrometer, do the ions have a positive or negative charge? So you use the second right-hand rule to do that. So they're moving this way. They come through this path down here. They're moving down. You know, they're going in a circular path. You know, the magnetic field is out. Now, remember, for circular motion, the force has to be towards the center of the circle. So no matter where you are, let me just pick a point over here. You're looking at the figure down here. If you're down here where the arrow is, the force is towards the center, right? When you go in a circle, that's be towards the center. So you, if V is this way, so V at this point is down, and B is out at you, the force is towards the center. Would that happen for a positive or negative charge? So do it for a positive charge, and if it works out, then it's a positive charge. If it doesn't work out, then it must be a negative charge. Okay, in a minute, I'll do a better picture with that. And then there's a part B to this. Let's see. If you're given this magnetic field, this speed, and 250 times the mass of a proton, what is going to be the point between where it enters and where it exits? So basically twice the radius. So if we can figure out the radius, multiply it by 2, we can figure out that's what this is actually giving you. This is the diameter of the circle. Okay, so let's take a look at this. Okay, so here's here's the path going in a circle. So like let me just pick a point here. This is the direction of the velocity. Now the magnetic field is out at you. And we know the force has to be towards the center of a circle. So there's the force. So use the right-hand rule, line those things up, V, B, and F. You've got all three, line them all up. And if it's if this is true, then it must be a positive charge. This is what would be happening if it was the opposite of what we have here, right? It would follow that kind of path. Okay, so if V, B, and F all line up, it must be a positive charge. If not, then it must be a negative charge. Okay, so you're moving, there's a magnetic force towards the center, and we're going in a circle. So remember, for circular motion, we had net force is ma. It's just when you're going in a circle, this is radial acceleration towards the center. We know that that's mv squared over r. And then in this case, what's the actual force? What's the magnetic force? Which is q v b, just the magnitude of the charge here. One of these v's actually cancel out. And then from this, we can solve for the radius. So when you read through the chapter, they came up with this formula for you. So we've got mv over here, and then there's a qb on that side. Let me put it back over here. And then that's equal to r. So this is how you can actually get the radius of this circle. And then they're actually asking for twice the radius. So solve for the radius, multiply it by 2, and I believe the answer was in centimeters, so you might have to convert it over to centimeters. Magnetic field strength was given in the problem. The speed is given. 255, in my problem anyway, times more massive than a proton. A proton is 1.673 to the minus 27. So you have everything here. You got the mass given, the speed's given, and from this then you can get the radius. Also, don't forget they said singly ionized, so you know the magnitude of the charge too. Okay, good, singly ionized. So that's what we have. And then from this, you can tell whether it's positively or negatively charged based on, does it do this or does it do that? They're telling you it does that, so to do that, does it have to be positively or negatively charged? All right, if you have any questions, just send me an email and I'll talk to you soon. Bye-bye.